So in this first video, I'd like to talk a little bit about measurements and motion. Physics is the scientific study of how things move and how their movement changes, and why things move and why their movement changes, and how objects interact with one another. So typically in a physics course, we start with a study of how objects move, which is called kinematics. But one thing that we want to get to before that even is to describe how objects move. We make measurements. In fact, we make measurements to describe objects before we even talk about their motion, like how big is this object, how heavy is this object, etc. So we want to start with a little conversation about measurements. Measurements are comparisons. When you measure the length, width, height of an object, as it says here, you are comparing it to a ruler or to a measuring tape. So if you say, I just went out for a 5K run, what you mean is I ran 5 times farther than a kilometer. In fact, what you mean is I ran 5,000 times farther than a meter. And the meter is our preferred unit. So if you tell me you went out for a 5K run, I know how far that is because I know how big a meter is. For our purposes, the length of a meter is how big a meter stick is. It was originally defined as 1/10,000,000th of the distance from the North Pole to the equator on a line that runs through Paris. And today it's been technically updated, the definition to be how far light travels in a certain amount of time. But those definitions are not, for most of us, more useful than to say a meter is how long this meter stick is. And so 2 meters means 2 meter sticks in a row. We know how big that is. And if someone says a distance is 5.2 meters, you know that means 5.2 times the length of this particular ruler that we call a meter stick. Well, I just want to make sure we're thinking about measurements as comparisons like that. Time elapsed is also measured in comparisons. If time elapsed is, it's usually multiples of or fractions of years and days. So if something takes an hour, we know an hour is defined as 1/24th of a day, and minutes and seconds as fractions of that. Technically, seconds are defined by physicists as according to the vibration of certain cesium atoms under certain conditions. Seconds are our preferred measurement, our base unit, and we can think of seconds as, for now, as just the amount of time that it takes a second to move on a clock. 3 seconds is 3 of those ticks. So that's the comparison that we're talking about. When you measure the mass of an object, mass is a topic that we're not going to get into in the first couple of videos, but when we do, the mass of an object is a measure of its inertia. And we compare an object's inertia and its mass. It says here the official kilogram. The kilogram used to just be this chunk of metal in Paris, and that much metal was called a kilogram. So if you had something that had a mass of 0.3 kilograms, you knew that it meant that it was 0.3 times the inertia of that particular official chunk. In 2018, they redefined the kilogram to be related to Planck's constant, which is really cool for a bunch of high-end research stuff. But for our purposes, a kilogram is just this chunk in the physics stockroom, this brass piece labeled 1 kg. And that's fine. For our purposes, if something is, for example, 8 kilograms, you know it has the same inertia as 8 of those. If I tell you that my mass is 80 kilograms, then you know that I have the same inertia as 80 of those little brass pieces that are labeled 1 kilogram each. The kilogram actually brings us to an interesting point about the base units in the metric system. We have these base units of things like meters and seconds, and kilogram is the only one that actually has a metric prefix in the base unit. When we talk about a base unit, what I'm talking about is the standard for measuring a particular quantity, and we measure things in these various units, but there are other units that are actually derived or calculated from the base units. So when you're talking about things like meters, you want to have all of your meter measurements converted from centimeters or kilometers to meters, so that when we plug them into various equations, our units for more complicated quantities come out in the proper units. Again, the one exception that you want to keep a metric unit is the mass. You want it in kilograms. The table here shows a bunch of different metric prefixes that we will use. I do not recommend that you memorize a bunch of them, though. There's no sense in memorizing the ones that you don't frequently use. Most of this class is science majors, so you're probably using certain ones already in your other classes in your major. I use kilo and mega a lot, and I use centi and milli and micro and nano a lot, but I don't use a lot of other prefixes, so I could be forgiven for not remembering the difference between femto and pico. What do you do if you get a problem and it has femtoseconds? Well, if you were doing a homework problem or you were at a cocktail party or something, you would look up what femto means, and you would see that it means times 10 to the minus 15th. We will be using the scientific notation like this to convert our metric units to the base units. You will therefore want a calculator or a emulator app that does scientific notation. I don't get paid to endorse this particular app, but it's a good app and it's free, and it's the one you'll see me using on the next couple slides here. So if you don't already have a scientific calculator, I recommend that particular app. You don't need a graphing calculator, but a scientific one. So let's do a example problem here. The whole point of the metric system is to be able to do this type of math with these prefixes relatively easily and quickly without having to memorize a lot of unit conversions. So things like there's 12 inches in a foot and 5,280 feet in a mile. Those are just awkward numbers. I'm sure you're familiar with the justification over the years. You've probably learned it a lot of times about why we use the metric system. The one time that you will need to continue using those awkward multiplication is we expect you to know there's 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute, and 365 days in a year. But everything else is going to be metric, base 10 type of things. So we'll get a situation like this. Determine the volume of a rectangular space that is 13.0 kilometers by 6.2 kilometers by 8.8 kilometers. So this is a pretty big rectangular space. The way I'm going to do this, I don't think I need to draw anything to start this problem. I could probably just jump straight into saying I'm going to need an equation for volume. If it's a rectangular space, the volume is the length times the width times the height. And if I didn't remember that, I would look it up. We will have the option to look up equations like that when we need them. So my setup is what I want to talk to you about today. My volume is going to be my length times width times height. So when I go to type these numbers in, I'm talking about 13.0. Notice it says kilometers up here, and I have replaced kilo with times 10 to the third. This is where you want to do that. You want to do that when you go to write these numbers out like this to do the math. So 13.0 times 10 to the third. How did I know it was times 10 to the third? Because that's what the K stands for. And if I forgot what times 10 to the a K is, I would just go look that up. Again, you'll be allowed to do that in this course. Times 6.2 times 10 to the third meters, because that's what 6.2 kilometers is. And then times 8.8 times 10 to the third kilometers. So that'll be our volume. I have this short video here to show you how I recommend you use the calculator when you're doing scientific notation. I am making this recommendation because a lot of students who are good at math try to use scientific notation on their calculators, and their calculator misunderstands what they're trying to do, and therefore what was set up correctly comes out with an incorrect answer. So I'd like to avoid that. And here's one of the things I would like to encourage you to do. Do not ever use this button that I'm pointing at right here, that little the caret, the raised to the power, for scientific notation. If you need to do something like 3 to the 6th power, that's fine. Do the 3, then that raised to the power, and then the 6, and you'll get it. That's fine. But for scientific notation, don't use that one, and don't use this one either. If you hit second, and there's a button down here, this one, second log, you get a 10 to the x. You might be able to make those things work, but those two methods, while they're not wrong, they lead to calculators being confused and giving you therefore wrong answers a lot. And you'll have to use a lot of parentheses to do it that way. What you might instead do is there is a capital E, usually 2 E's on these scientific calculators. So as I'm typing this in here, I'm typing in the 13.0 second, and then I hit the comma. On different calculators, like if you have Casio or something, it'll be in a different spot, but you'll be able to find a place where you see usually capital E, not lowercase e. That's very different. That's a stats exponents type of number. That capital E, I believe stands for engineering exponent. Your calculator understands it to mean times 10 to the. So right now, my calculator thinks I've typed in 13.0 times 10 to the third. And that's what I want it to think. And I don't need to worry about any parentheses or anything. If I type in a times or a divided by or anything right now, it doesn't assume that that multiplication is happening in the exponent, which can happen if you're using the this button here. So this is my recommendation for how you type these things in. So times 6.2 capital E 3. That's 6.2 times 10 to the third. Times the 8.8 times 10 to the third. And that's how I will pronounce capital E, is times 10 to the. And so that gives me an answer of 7.0928 times 10 to the 11th. That was, my volume is 7.09 times 10 to the 11th meters cubed. That E, for my class, you may report your answers with that capital E instead of the symbols for times 10 to the. Not every professor out there would probably be okay with that, so you might want to check with them if you're ever in another class and you want to do that, but there's nothing wrong with it. That's what the capital E means. So that's the end of this video. I want to point out that we're sort of glossing over parts of the OpenStax Chapter 1 that talk about things like significant figures and accuracy and precision. Some of you may have grimaced a little bit when I rounded this off to 7.09 and didn't explain how I knew where to round it off. That's because I don't want to make that a point that we're really focusing too much on for this course. I want to get into the physics of what we're doing. And there is a right way and a wrong way to do significant figures, and I just don't want it to be our focus.